What I want to do in this clip is a bunch of examples of calculating double integrals using iterated integrals on simple domains, which are no longer rectangles, obviously. Those are too simple. So here's the first example. Suppose our domain is the following. So here's our domain, bird's eye view of the domain. Here's the line, which is y equals x over 2. Here's the line y equals x, and I'm looking all the way to x equals 4. So this is x equals 4, and my domain is this triangle that I got inside here. And tell me if you agree, so this is D. Tell me if you agree that this domain is simple. For example, I can allow the x's to range between 0 and 4, and then for each x, the y's range between x over 2 and x. Does everybody see that this is a simple domain? Do you agree? Now I can calculate the integral. I just have to tell you what the function is. So the function that we're going to be looking at is the function x to the power 3 plus y to the power 3. That's f. So what is the double integral over the domain D, this triangle, of this function? X cubed plus y cubed dx dy. So I'm going to write it as an iterated integral. It's a continuous function on the entire plane, so everything is nice and safe in terms of the conditions of the theorem. So I can write it as an iterated integral. The outer integral is going to be from 0 to 4 dx. The inner integral is going to be y equals x over 2 to y equals x of the function x cubed plus y cubed dy. Do you agree? So this is precisely using the theorem. I left it here on the board. We have a simple domain. F is continuous on the domain. The double integral equals the integral between the two ends of the segment in terms of the x. So a and b in our situation were 0 and 4. Integral from 0 to 4 dx. The inner integral is the integral dy between the two functions that define the bounds for each y, okay, of the function. Clear? Does everybody see that this is precisely the theorem? Okay, and now I'm going to calculate this, and this is from this step, this equality was a Calc 2 statement. It was that theorem. Everything from here on is entirely Calc 1. I'm just calculating integrals in one variable. You see here 2 snakes, but I'm doing them one at a time. Okay, it's entirely Calc 1-ish. Okay, so how do I calculate this integral dy? I use the Newton-Leibniz formula. I find the antiderivative calculated between the bounds. Okay, so let's do that. I always work my way out. Start from the inner integral and calculate my way out. Here there are only 2, but later there are going to be 3. So from 0 to 4 dx, I'm leaving this untouched. What's the antiderivative of this with respect to y? It's x cubed y plus y to the power 4 over 4. Do you agree that this is the function whose derivative with respect to y is this? So this is the antiderivative of this with respect to y. X is now fixed. X is a parameter. Good? And I have to evaluate it, this is the Newton-Leibniz formula, between y equals x over 2 and y equals x. Clear? And everything, do the integral dx. Clear? Good? My suggestion, just a suggestion, always write this. Don't just write between x over 2 and x. Write between y equals x over 2 and y equals x. It's a bit more writing, but it pays off. And the reason is that you don't make mistakes and plug in things where they don't belong. And it becomes even more confusing and more crucial when you have 3 variables. Okay, so always use the full detail of writing which variable equals which. Okay, so I'm going to plug in y equals x here, minus plug in y equals x over 2. So what do I get? I get the integral from 0 to 4 dx, that I didn't touch yet. And then I'm plugging the upper bound, so I get x to the power 4 from here, plus x to the power 4 over 4, when I plug y equals x here, minus, and now the lower bounds. When I plug x over 2 here, I get x to the power 4 divided by 2. And again minus, when I plug in x over 2 here, I get x to the power 4 divided by 2 to the power 4, which is 16, and divided again by 4, which is 64. So minus x to the power 4 divided by 64. At this point, I have to verify that there are no more y's around. If there are still y's around, something I'm doing wrong. Okay? I found the integral dy, I plugged in the values. This should be just an expression in x's. Okay? Do you see that what I'm doing is completely single variable calculus? I'm just doing them one by one, but there's only single variable calculations and ideas and theorems going around. You may need to use, in further examples, more complicated theorems from complicated. Like you may need to do a change of variables, or substitution, or I don't know, integration by parts, or you may need to, here it's just completely elementary, but it's always going to be just Calc 1, except for this first step. Clear? Okay, what about this? So this is an x to the power 4, and I can pull out all these coefficients, and I can do a common denominator, right? So what I get, I really don't want to move to another board because we're almost done. So this equals, so it's 1 plus 1/4 minus 1/2 minus 1 over 64. And if you do a common denominator, you'll see that what you get is 47 over 64. And you can pull that out of the integral. And then you have the integral from 0 to 4 of x to the power 4 dx. So it's 47 over 64, x to the power 5 over 5, where x is between 0 and 4. And that equals 47 over 64. When you plug in 4, you get 4 to the power 5. Let me just leave it as 4 to the power 5 divided by 5. That's the answer. You can simplify it a bit. 64 is 4 to the power 3, right? So these two cancels, and you just have a 16 left here. And 16 times 47 is 752. I'm cheating. It's on my notes. And that's the final result. Good? Everybody? Is the idea clear? Let's do another example. Example number 2. So let's look at the domain now. The domain now is going to be the following. So in many cases, you're not going to have the domain drawn for you. You're going to have to figure it out. Okay, so let's figure out a domain. Let D be the region bounded between y equals 1, x equals y squared, and x plus 2y plus 1 equals 0. And what we want to do is find the area of D. So first let's understand what D is. So here's D. This is the x-axis. This is the y-axis. Y equals 1 is going to be up here somewhere. This is y equals 1. X equals y squared is a parabola that looks like this. Do you agree? X equals y squared. It's not y equals x squared. So it looks something like this. This is x equals y squared. Do you agree? Has to be symmetric. And x plus 2y plus 1 equals 0. That's another way of writing 2y equals minus x minus 1, or y equals minus 1/2 x minus 1/2. Do you agree? Everybody? And that is just a straight line, and I know how to draw it, so it has to have slope minus 1/2 and cross it minus 1/2, which is, so this is 1. So minus 1/2 is going to be here, and slope minus 1/2, so it's going to look something like this. This is the graph of a straight line, so I'm going to make another effort to make it straight. Okay, that's somewhat better. Big blur here. Okay. So our D is this kind of, think of a long spear, this kind of arrowhead of the spear. This is D. Do you agree? D is this. This blue has to say goodbye. Goodbye, blue. Thanks for your service. Do you agree? Okay, so this line was this. Okay, so before we calculate integrals, which are not obvious because I don't see any snakes here on the board at the moment, but there's going to be some in a minute, is D a simple domain? So it has to be a conditioned yes and no. The answer, okay, the correct answer is yes, but you have to specify. It's obviously not simple like this. Do you agree? You can say that the x's are fixed between two values. By the way, you can find these values. So these values of the intersections here are 1. It's not very clear from the picture. This is the true situation. Okay, they intersect at 1 here, and this is -1 and this is 1. You can set them equal and see what you get as a result. So if you look at, for example, this x here, if you look at this x here, it's not a simple domain. You're going into the domain, out of the domain, and then into the domain again, and out of the domain again. So the y's for this specific x do not live between two fixed functions. Do you agree? So it's not simple in that direction. However, it's still simple because it's simple in the other direction. If you allow the y's to be fixed between y equals -1 and y equals 1, and for each y, the x's to range from here to here. Do you see that when looking at it like this, it is in fact a simple domain? Does everybody see that? Okay, so for each fixed y between -1 and 1, the x's range between x equals, so y's are between 1 and -1, and the x's are between this bottom function, and I'm saying bottom because I'm looking at it like this, the bottom function is x equals minus 2y minus 1. And the top function is x equals y squared. Do you agree? Okay, so this is a simple domain. This is D. Now, what does this very nice drawing and colors and observations and so on, what does this have to do with calculus 2? Good question, huh? We want to find the area of this domain. Do you agree that it can be done by means of single variable integrals, right? We can take this triangle and then calculate the area under the graph and do things like, but everything is going to be single variable, okay? But I can do it in two variables using a certain idea which repeats itself often, and that's why I want to present it. Think of the function, the constant function, fxy equals 1. That's a perfectly legitimate two-variable function. Do you agree? fxy equals 1. Where would be the graph of that function? It would be just up here. Do you agree? What's the double integral of the function 1 over the domain D? The double integral of the function 1 over the domain D is the area of the domain times the height. The height is fixed, it's 1. So the double integral of the function 1 over this domain is precisely the area of the domain. If you were doing it in units, you'd get the area in units of volume. But since we're just thinking of the numbers, it doesn't matter. And that's true in general. If you want to find the area of a certain domain, here's a domain down here on the floor, take the function 1, calculate the double integral of the function 1. It's going to be the area of the domain times 1. So it's just going to be the area of the domain. Does everybody get that? Good? Okay. So the area of D equals the double integral over D of the function 1. And this is true in general. This is not just for this example. This is true for any domain D in the plane. Does everybody agree to this? Do you understand why this is true? Okay. So let's do it for this example. So in our example, the area of D, which we want to calculate, is the double integral over D of the function 1. And now I want to write what D is. So here I'm going to calculate this double integral using iterated integrals. So the y's go between -1 and 1. That's the outer integral. The inner integral, the x's go between x equals minus 2y minus 1 and x equals y squared of the function 1 dx. That's writing that domain as an iterated integral, and the f is just the function 1. Good? Everybody? Okay. Now we're back to Calc 1. We're just calculating single variable integrals, doing them one by one. So the outer integral I leave untouched. We only get to that after we solve the inner integral. What's the inner integral? What's the antiderivative of 1? X. Evaluated between x equals minus 2y minus 1 and x equals y squared. All of this I have to integrate dy. So I get the integral from minus 1 to 1 of, plug in the upper value, y squared, minus, plug in the lower value, minus 2y minus 1. And integrate all of this, dy. At this point, after I solve the integral dx, there should be no x's left. It should be all y-ish, and it is. So this is the integral from minus 1 to 1, y squared plus 2y plus 1 dy, which in turn equals y cubed over 3 plus y squared plus y evaluated between -1 and 1. When I plug in 1s, I get 1/3 plus 1 plus 1, which is 2 plus 1/3. It's 2 1/3, which can be written as what? 7 over 3. And then minus, when I plug in -1, I get minus 1/3 plus 1. So it's 2/3. No, sorry. Yeah. Minus 1. So it's minus 1/3. So it's minus 1/3. So it's plus 1/3. And the total is 8 over 3. Is that true? Yeah. Good? Questions?
When you say that the function is like equal to 1, fxy is equal to 1, it's like a plane within the domain.
The graph of the function?
Yeah.
The graph of the function is just a plane at z equals 1. Okay, and the volume under the graph of that function over a domain D is just the area of the domain times 1, which is just the area of the domain if you disregard units. Okay, if you're going to be working with units, you're going to get volume, so you're going to get centimeters cubed, whereas what you want is just the answer in centimeters squares. Okay, but more questions? Is it clear what just happened, what we did? Okay, is it clear that in this case, this domain is only simple if you look at it from left to right, and is not simple if you try to look at it from bottom to top? Clear? Okay. Let's do one more example in this clip, which is going to lead us to the idea of the next clip. So this is a neat example. It's an example I like. So this is example 3. Here's the function. fxy is going to be the function e to the power minus y squared. Okay, so it's a function of two variables, which just doesn't see x. So it's the same for every value of x. Okay, and the domain is going to be the following. So I'm going to look at the box, the 1-by-1 box here. And I'm going to look at y equals x, which is this. And the domain is going to be this upper triangle. That's the domain D. Okay? Good? Now, do you agree that it's a simple domain? If I let the x's range between 0 and 1, and for every x, I let the y's range between the bottom of the triangle and the top of the triangle. Do you agree? So what's going to be the double integral of f over this domain? It's going to be the double integral over d of f. Let's write it as an iterated integral. So I'm going to write the integral from 0 to 1, dx of the integral from what? From y equals x up to y equals 1 dy, do you agree? Of the function e to the power minus y squared. Does everybody agree? And from here on, it's just Calc 1 stuff, right? It's calculating single variable integrals one by one. Do you agree? Problem, there's a little issue here. Usually when we say from here on it's Calc 1, that's the point where you should say, ah, okay, easy, let's do it later. Or we know how to do it, forget it. Here, there's an issue.
We're going to get something over x, and x is going to equal 0.
Before the we're gonna part of your statement, start. Start. How do you start? You start from the inner integral, right? What do you have to do? You have to find the antiderivative of this, plug in the values, right? E to the minus y squared, so by the looks on your faces, I understand that you haven't been told that. E to the minus y squared is one of those functions, and there are several of them, that looks very naive, but does not have an elementary antiderivative. Not that we don't know how to calculate it, it doesn't have one. It's a continuous function. It has an antiderivative, but it's not elementary. Okay, so there's no elementary expression in terms of exponents and logarithms and trig functions and radicals and whatever. There's no elementary function whose derivative is e to the minus y squared or e to the minus x squared. Okay, so we're stuck. We don't know how to calculate this. Okay? We can't do Newton-Leibniz, because Newton-Leibniz tells you find the antiderivative, plug in the values. No antiderivative. Fatal error termination. Don't know how to proceed. Clear? Oops. Okay? Do we give up? Never give up. Do you agree? So here's the nice little magic that happens with this example, and it's a classic example. Do you agree that this specific domain is simple with respect to the y variable as well? So it's also simple if I think of it like this. Do you agree? So this same integral, the double integral of f, can be calculated as, let's do it carefully, the integral from 0, look up here a second, the integral from 0 to 1, and this time it's the one on the y-axis, dy, that's the outer integral now, of the integral dx of the function, where x ranges between x equals 0 and x equals y. Do you agree that this is the way of writing the same double integral as an iterated integral in the other order? Do you agree? Everybody? Now this I can calculate. Why? Let's do the inner integral first. What's the antiderivative of e to the minus y squared?
Minus y squared x.
Right. We just said there's no antiderivative to e to the minus y squared with respect to y. But with respect to x, this is just a constant. Its antiderivative is x times the constant. This is a 7, a 15. The antiderivative of 15 is 15x. The antiderivative of this is x e to the minus y squared. Do you agree? Evaluated between x equals 0 and x equals y, and all of this integral between 0 and 1 dy. Do you agree? Everybody? And it looks like I've just postponed I'm eventually going to have to handle this e to the minus y squared. It looks like I've just postponed it and I'm going to run into it in the next step. But I'm not. I'm not going to have that issue. And let's see why. Let's see why. And that's the answer. When I plug in x equals y, I'm going to get a y here. When I plug in x equals 0, I don't get anything. So it's the integral from 0 to 1 of y e to the minus y squared dy. Do you agree? And this function not only has an antiderivative, but in fact, it's almost an immediate integral. For me, it is. If you don't see it, you may need to do an extra step of a substitution or something. But I just see that this is the derivative of e to the minus y squared. Because what's the derivative? Up to a constant. We're going to have to fix it. What's the derivative of this? It's the derivative of e to the something is e to the something times the inner derivative, right? So the derivative of this is e to the minus y squared times minus 2y. But I just want the y, so I have to multiply by minus 1/2. Do you agree? And the derivative of this is now precisely that. And I have to evaluate it between y equals 0 and y equals 1. Good? So when I plug in y equals 1, I get, so let's put the minus 1/2 outside here. I get e to the power minus 1, which is 1 over e, minus e to the power 0, which is 1. And that's the answer. Questions? Cool, huh? Neat. Okay, so this leads us to the idea that I want to discuss at more length in the next clip, that sometimes you can change the order of integration. That's what happened here. Instead of integrating dx and integral dy, I integrated dy and integral dx. Okay? So when can you do that? When the domain allows you to do that. And that's the idea of changing order of integration. And there's a theorem there called Fubini, which is nothing new. It's just taking a different perspective on the theorem we already know. But that I want to discuss in the next clip and do a more interesting example. Here, looking at it like this or like this was just as obvious, right? The domain was easily seen to be simple with respect to both variables. Okay? So changing order of integration in the next clip.